So this is the 23rd session on rigid body kinematics. Okay. So before going into details of this video, first I would like to state that the videos which I am making for physics and uploading on YouTube, if you go through them, if you study them properly, then you don't have to go to any other coaching institute, or you don't have to refer to any other book also. Okay. You can just read from these videos of YouTube and then your preparation will be complete. For NEET and JEE Mains Advanced both. This I would like to make it very clear, okay? So that is the purpose of making such videos, that you can read from these videos itself, you can prepare for JEE Advanced and NEET, okay? So this I'm making very clear, alright? So keep this in mind, okay? And tell your friend also, to others of your acquaintance and friends also, to refer to this video. They can study this, and in free you can study, okay? So that will be a great help, okay? So now I'll take up this 23rd session on rigid body kinematics, okay? So in this I'll take up the third chapter on rigid body kinematics, namely the acceleration equation for rotating rigid body. Okay. So, so in this, basic what we are going to do, what we are going to discuss is this. That is, we are given some rotating rigid body, and we know that when a body rotates, rigid body rotates with respect to some given frame, then in general at a given instant, two locations of this body do not have the same acceleration, okay? So suppose we are given a rigid body which rotates with respect to some given frame f, and we are given a location p1 of this body whose acceleration with respect to f is given, and we have to find the acceleration of some other location p2 of m with respect to f. Then how to do that, okay? So that how to find this, that we'll discuss, okay? So first I'll write down the general equation, okay? Then I'll take up the further details, all right? So this is a given reference frame f. This is some given rigid body m which rotates with respect to frame f. At some instant of time, omega is the angular velocity of m with respect to f at time t, and beta is the angular acceleration of m with respect to f at time t, and p1 and p2 are two locations of m, okay, fine. R is the relative vector of p2 with respect to p1, okay. Acceleration of p1, velocity of p1 with respect to frame f at time t is v1f, and velocity of p2 with respect to frame f at time t is v2f, and acceleration of p1 with respect to frame f at time t is a1f, and acceleration of p2 with respect to frame f at time t is a2f. So all these quantities are shown arbitrarily, okay. One more thing should be noted, that we know that in general, if a point moves, then at a given instant, its velocity and acceleration do not have in general have the same direction. So they have been shown in different directions, okay. R is a relative vector, okay. So all these quantities are given. Now, in the in the second video on rigid body kinematics, I discussed the relationship between V2F and V1F, okay. So in that video, the result was derived. If you want to go to that second video, you will get all the details, okay. So the result was this: V2F is equal to V1F plus omega cross R, okay. This was termed as the velocity equation for a rotating rigid body, okay. This was termed as the velocity equation for a rotating rigid body, alright, fine. This equation is valid for all time instants, okay. Now this, now what we do, one more thing, this formula is valid for plane and 3D rotation of m with respect to f. This is general formula. It is valid in both cases, when m rotates with respect to f in a plane fashion or in 3D rotation. In both cases this formula is valid, okay. Now what we do, we differentiate this equation with respect to time in frame f, okay, both sides. So since it is valid for all times, we can differentiate it, okay. So this will write as dv2f by dt in frame f is equal to dv1f by dt in frame f plus d by dt of omega cross r in frame f, okay. Now this quantity we know from the theory of particle kinematics, that is nothing but acceleration of p2 with respect to frame f at time t. This quantity we know from the acceleration stream theory. This quantity is a1f, that is the acceleration of point p1 with respect to frame f at time t. Now this we differentiate using the product rule of calculus, and since cross product is non-commutative, so we have to maintain the order of the terms. This becomes d omega by dt in frame f cross r plus omega cross dr by dt in frame f. Okay, so this becomes a2f is equal to a1f plus this becomes beta, angular acceleration of m with respect to f at time t, this quantity, time derivative of angular velocity. So that becomes beta cross r. Now plus, or this term is split by that formula, dA by dt in frame f equal to dA by dt in frame m plus omega cross a. So this term is split in that way. So this becomes dr by dt in frame m omega cross r. Okay. Now this term becomes 0. Why? Because P1 and P2 are two locations of M. So P1 and P2 are fixed with respect to body M. And vector R is a vector from P1 to P2. So as seen from frame M, this vector R is a constant vector. And time derivative of a constant vector is 0. So this term goes away. So what we get is this. A2f is equal to A1f plus beta cross R plus omega cross R. Okay, so this is called the acceleration equation for a rotating rigid body m with respect to f. We'll call this equation as acceleration equation of rotating rigid body m with respect to f. Acceleration equation of rotating rigid body m with respect to f. Acceleration equation of rotating rigid body m with respect to f. So this formula is valid for both cases, 2D and 3D rotation of m with respect to f. General formula, it's always valid, okay? It is valid both for (2D) and 3D rotation of m with respect to f. Okay, so this formula relates the acceleration of 2 points, 2 locations P1 and P2 of a body m, rigid body m, which rotates with respect to some given reference frame f. Okay, so it's valid in both cases. Now, see one thing, in case m undergoes 3D rotation with respect to f, then to find A2f we have no option but to use this formula. Suppose R is given in IJK notation, omega is given in IJK notation, beta is given in IJK notation. By using this formula we can get A2f. Okay. But suppose M undergoes plane rotation with respect to f. Okay. Plane motion, plane rotation, as we have been talking in previous videos also. Suppose M undergoes plane rotation with respect to f. Then also by using this formula we get A2f. Again we have to find, we are given R, omega and beta in IJK notation. So we have to evaluate this cross product and add all these three terms to get A2f. But that procedure becomes very lengthy because evaluation of cross product in IJK notation is a bit of time consuming. So we would not like to write in this way. In for plane motion case of m with respect to f, we would like to convert it into a scalar form, as we did in case of a velocity equation, SRC procedure for velocity, as was discussed in the seventh video, most probably 7th or 8th video. You go to that, you get it all the details. Okay. So now we are interested in that case. M undergoes plane motion with respect to f, and P1 and P2 are two locations of m in the same base plane. In that case, we would like to convert it to a scalar form so that the time for calculating these terms is minimized, just to minimize the time calculation. Okay, to minimize the time taken. Okay, so to convert this into a scalar form for a case when m undergoes plane motion with respect to f, and P1 and P2 are two locations of m in the same base plane. Locations of m meaning that P1 and P2 are in the same base plane. Alright, P1 and P2 are in the same base plane. Location meaning they are fixed with respect to f, m. They can be either real location or imaginary location of m. Okay. So to convert this scalar form, scalar version for the case when undergoes plane motion with respect to f and p1 and p2. So this I'll write it, okay. Are two locations of M. And when I say location, it can be real or imaginary. In same base plane. In same base plane. Okay. So to convert this vector equation into scalar form, for the case when M undergoes plane motion with respect to F, and P1 and P2 are two locations of M in the same base plane. Two locations, they can be real or imaginary location. Alright. This is our M. Now one thing should be noted before going ahead. Let's suppose P is a point which moves in a circle with C as the center, R is the radius. Okay. Then suppose the sense of angular velocity is omega. The velocity of P will be omega r at right angles to line radius Cp, corresponding to sense of omega. Omega is anti-clockwise, omega should be in this way. Omega is clockwise, omega should be in this way. Alright, fine. So one more thing you must know that suppose I will draw C is the center of circle, R is the radius of circle, P is a point which moves in a circle. Suppose angular speed of circular motion is omega, anti-clockwise, just assume for the sake of argument. Suppose angular acceleration of circular motion is beta, that is also assumed to be anti-clockwise. Then acceleration of P will have is a resultant of centripetal acceleration, omega square r, or v square by r, where v is the speed of point P, where v is just omega from circular motion theory. And tangential acceleration of B will be r beta. And centripetal acceleration of P will be omega square r towards center. So net acceleration of P will be the vector sum of these two, omega square r and r beta. This is called the tangential acceleration. And this is called the centripetal acceleration, AC. And this is called the tangential acceleration. All these things I have been discussed in great details in the videos on circular motion kinematics. If you go there, you will get all those things, okay? If you open that playlist, then you get all those things, okay? In this I showed beta in this way. Suppose sense of omega and beta are opposite. Suppose sense of omega is anti-clockwise, sense of beta is clockwise. P is a point which moves in a circle. Since omega is in this sense, so speed should be in this sense, linear speeds omega r. In this case, acceleration of P will have two components. A centripetal component AC, which is v square by r or omega square r towards center. Beta is in this sense. Tangential acceleration AT will be equal to r beta. So net acceleration of P will be the vector sum of these two accelerations. So this point I have stated because this will be used here. Okay, fine. Now this I'll grab it. Also, you know from the theory of relative acceleration between 2 points P1 and P2, A P2 P1 slash F, acceleration of point P2 with respect to point P1 in frame F is equal to A2F minus A1F. A2F denotes the acceleration of P2 with respect to frame F, and A1F denotes the acceleration of P1 with respect to frame F. And this is the relative acceleration of P2 with respect to P1 in frame F. Alright, this is general formula. It has nothing to do with rigid body, or it is always valid for any 2 points. Okay. This also has been discussed in great detail in the videos on relative velocity. If you go there, you will get all those things. Okay. Now, as I derived the acceleration equation here, I'll write it again. A2F is equal to A1F plus beta cross R, in this case for rigid body, rotating rigid body, plus omega cross R. So if you see, this becomes A2F minus A1F becomes how much? Beta cross R plus omega cross R. We're comparing these two terms. This term itself is this term. This term is just the term A2F minus A1F. This term is this. Beta cross R plus omega cross R, that is the term A2F minus A1F. That is the term A2F minus what? A1F. Beta cross R plus omega cross R, that is A2F minus A1F. Alright. So, we'll write this equation in this way. This term is this term. This term itself is AP2 P1 slash F. So from this we see that A2F is equal to A1F plus AP2 P1F. This quantity denotes this quantity. So now see, suppose we are given this term, we are given this term. We add these two terms, we get this term. Okay. So suppose this we are given, and this we have to find. We have to take 3 actions. 3 actions have to be taken. Action 1. Give the acceleration of P1 with respect to P2. See, acceleration of P2 with respect to frame F is the vector sum of these two. If we impart these two accelerations to P2 and add them vectorially, we get the acceleration of P2 with respect to frame F. Alright, fine. So, first action is what? We give the acceleration of P1 to P2. Or we say another words, P2 is assumed to move with the acceleration of P1. This doesn't mean that acceleration of P2 is equal to that of P1. It simply means that we are evaluating the first term. Okay. So, what action we are going to take? Give the acceleration of P1 to P2. That is, you give this term. Okay. First action has been done. So this I'll grab it. Okay. First action is this. Okay. Now I take the second action. Second action. The second action is evaluation of this term without using that determinant notation IJK method. That is very lengthy. We have to evaluate these two terms in easier way. So the time calculation is minimized. Okay. So action 2 is what? Action 2 is what you must understand. See, suppose P moves in a circle with C as center and R as radius. Suppose. This means C is fixed. If P moves in a circle with C as center, then C should be fixed. Okay. Distance CP is constant. That is equal to radius of the circle. P and C are confined to remain in the plane of circle. C and P are confined in the plane of circle. And remain in the same plane, sorry. That is in plane of circle. So, if P moves in a circle with C as center, this means C is fixed. Distance CP is constant equal radius of circle. And P and C are always confined to remain in the same plane, that is in the case of plane of the circle. Conversely, if C is fixed and P is a moving point such that distance CP is constant, P and C are always confined to remain in the same plane, then P will move in a circle. Fine, I'll repeat it once again. If P moves in a circle with center at C, C is fixed, distance CP is constant, and P and C are always confined to remain in the same plane. If we take the converse phenomena, if P moves in such a way such that distance of P from a fixed point C is constant, P and C are confined to remain in the same plane. I'll repeat it again. Conversely, if P moves in such a way such that distance of P from a fixed point C is constant and P and C are confined to remain in the same plane, then P moves in a circle with C as the center. Fine. Is it clear what I've said? I'll just repeat it once again. If P moves in a circle with C as center, C is fixed, CP is constant, or C and P are confined to remain in the same plane, that is in the plane of circle. If we take the converse phenomena, P and C are 2 points, so that C is fixed, CP is constant, and P moves in such a way such that C and P always lie in the same plane, then P moves in a circle with center at C. Now this concept we apply in this case. Instead of C, we take P1, and instead of P, we take P2. Okay? Instead of C, we take P1, and instead of P, we take P2. Alright? So now see, we have to evaluate this term, acceleration of P2 with respect to P1 in frame F. Now see, with respect to P1, P1 is what? Fixed. Since P1 and P2 are the two locations of a rigid body M, distance between P1 and P2 is constant, equal to R say. And by assumption, P1 and P2 are confined to remain in the same base plane. This means, as seen from P1, P2 should move in a circle. Fine. Is it clear? I'll just repeat it once again. With respect to P1, P1 is fixed. Distance P1 P2 is constant because P1 and P2 are two locations of rigid body M. And the distance between two locations of any rigid body M is always constant. And by assumption, P1 and P2 are confined to remain in the same base plane. That is, with respect to P1, P2 moves in a circle with center at P1 and radius R. Okay, so this will mean that acceleration of P2 with respect to P1 in frame F is a sum of two terms, a centripetal component and a tangential component. Alright, so this side of it, okay. So, as I stated just now, explained just now, with respect to P1, P2 moves in a circle of radius R, whose omega is same as the omega of M with respect to F, and whose angular acceleration is same as angular acceleration beta of M with respect to F. Alright, so second term evaluation becomes much easier. We don't have to carry out this IJK method calculation using determinant notation, which is quite lengthy, time taking, okay. So, in this case, suppose P1 is here, P2 is here, R is the distance. Suppose this is the sense of omega, this is the sense of beta, angular acceleration. So, acceleration of P2 with respect to P1 is the sum of two terms. A component omega square R towards P1 and a component R beta tangential to circle corresponding to sense of beta. Okay, so A P2 P1 F, that is acceleration of P2 with respect to P1 in frame F, is the vector sum of these two terms. E1 hat plus R beta into E2 hat. So see, E1 hat is a unit vector from P2 to P1 and E2 is a unit vector corresponding to sense of beta and tangent to the circle at P2. So this term has the evaluation has been greatly simplified. So action 2, what we have to do? What we have to do in action 2? I have explained in action 2 what we have to do. So in action 2, we will have to take two actions. Give first an acceleration omega square r to P2 towards P1, all right, and second an acceleration r beta tangent to the circle r beta perpendicular to line P1 P2, perpendicular to P1 P2, acceleration r beta to P2 perpendicular to P1 P2 and corresponding to the sense of beta, corresponding to the sense of beta. Perpendicular, why? Because it is tangent to the circle. So by property of circle, tangent to circle at any point is along the radius, perpendicular to radius at that point. So this we have to do action 2. Okay. Second action we have completed. I'll rub this one. So in this see, 4 possible cases arise. Omega and beta are both clockwise. Omega is clockwise, beta is anti-clockwise. Omega anti-clockwise, beta clockwise. Omega anti-clockwise, beta anti-clockwise. In all the 4 cases, what action we have to take in second action? The cell state. So suppose the sense of beta, omega is clockwise and beta is also clockwise. Both are clockwise. This is P1, this is P2. So in action 2, omega square is always towards P1, irrespective of whether omega is clockwise or anti-clockwise. It has nothing to do with the sense of omega. Now beta is clockwise, so in this r beta will be like this. Okay. Now suppose omega is clockwise, beta is anti-clockwise. So this is the situation, something like this. Omega square is still towards P1. It has nothing to do with the sense of omega. And r beta in this case will be in this sense, like this. Suppose omega is anti-clockwise, okay? This is C center, sorry, P1, this is P2. In this case also, beta is also suppose clockwise. In this case also, omega square is always towards P1. Beta is clockwise, so r beta will be in this sense. And last case, omega is anti-clockwise, beta is also anti-clockwise. So in this case, it will diagram will be like this. This is P1, this is P2. So in this I give omega square r to P1 and r beta will be in this way. Okay. So in second action, depending on these 4 cases, this is how we have to show the accelerations to P2. Okay. So this was the second action. Alright. So what is the advantage of second action? You can see. Advantage of second action is that we don't have to use that lengthy IJK method of determinant notation to evaluate those 2 terms. So this has been done in much easier way. So this is much more preferable method. Okay, fine. Now this error bit now. And third action, what we have to do? We have to simply add all those 3 terms. First action we give one acceleration A1 F2 P2, and in action 2 we evaluated 2 terms, we gave 2 accelerations we given. In third action, we have to add all these three terms, vectorially to get the acceleration of P2 with respect to frame F. Okay, this I'll rub it now. This also I rub it. And action 3, what we have to do? Vectorially add all the three terms given to P2 to get the acceleration of P2 with respect to F at given instant. Vectorially add the three accelerations given to P2 to get A to F. Okay. This is a three-step procedure again. Action 1, action 2, action 3. Fine. Now see. Again I'll draw the diagram. See, this is the frame F. Okay. This is the frame M. Rigid body M. Okay. It's undergoing, say, plane motion. I've taken omega and beta both to be anti-clockwise sense just for the sake of argument. Suppose P is some location of this M. P1, P2, P3, P4, etc. The other locations of M in the same base plane. P and all these locations, P1, P2, P3, P4 and P, they're all in the same base plane. Okay. Vector from P1 to P is R1. Vector from P2 to P is R2. Vector from P3 to P is R3 and so on. Okay. Now if you write P in terms of P1, acceleration of P with respect to P1, like this we say APF equal to A1F plus APP1 in frame F. This is common. If you write P in terms of P2, A2F plus P2 in frame F. Okay. What is this quantity? This quantity is simply beta cross R1 plus omega cross R1. Now this term is what? Beta cross R2 omega cross R2 in this way. Alright, fine. This also I'll grab it down. Similarly, write APF in terms of A3F. APF is equal to A3F plus APP3F. This quantity means what? Beta cross R3 plus omega cross R3 in this way. Okay. Similarly, write APF in terms of A4F. Then we'll write that as A4F plus APP4F, where this term means what? Beta cross R4 plus omega cross R4 in this way. Okay, fine. In this way, right? So now, what is the first thing? Suppose we know the accelerations of P1, P2, P3, P4 with respect to F, and we have to find APF. And what is the first thing which we have to do? First thing here, we see all these APFs are same. So now we have to decide which point other than P1 we should select, such that using that acceleration of that point we get the acceleration of P with respect to F. So if you use this equation, then by selecting P1 we can find P, AP. If we use acceleration of P2, then by using this formula we get the acceleration of P. Or if we select P3, then using this acceleration formula we get APF. If we use P4, then using this term formula we can get APF. So first action is what? First action is selection. Selection is the first action. First action is selection. Okay. What action we have to do in selection? In selection, what action we have to take? What action we have to take in selection? Select a point Pi, say, of M. Okay. Suppose acceleration of Pi with respect to frame F is AIF. I may be 1, 2, 3, anything, integer. Okay. So select a point Pi, say, of M. And this term is given. AIF is given. Okay. So now in this case, what we'll say that Pi is the selected point and P is the other point. Other point will short and write as OP. And Pi is the selected point. SP meaning selected point. And OP meaning other point. Pi is the selected point, P is the other point. Now what action we have to take? We give the acceleration of selected point to the other point. Give the acceleration of SP to OP. SP meaning selected point, OP meaning other point. So give the acceleration of SP to OP. Okay. Give the acceleration of SP to OP. This is the first action. So the first action is selection. So in selection, what we have to do? We have to select a point Pi of M whose acceleration with respect to F is known. And we write SP arrow Pi, OP arrow P, or Pi arrow SP, P arrow OP, whatever you write. And we give the acceleration of SP to OP. First action is completed. Alright, this okay. Now second term is what? Second term is the evaluation of that term. Beta cross R plus omega cross R. That is just the rotation term. And second two we will call it as rotation. This what action we have to take? Give the following two accelerations to OP. सबके से give omega square R to OP towards SP. That's the promotion case which I discussed in action 2 now. That's what I'm doing. And B, give beta R to OP perpendicular to line joining SP and OP corresponding to the sense of beta. To the sense of beta of M with respect to F. This is the second term, is a rotation term. Okay. And lastly, this alphabet. And lastly, what we have to do? We have to vectorally combine the three accelerations given to OP in the first A and B steps to get the net acceleration of OP. Fine. So what is going to be the third step? Third step will come as combination. In short, we'll write as C. And what action we have to take in the third step? Vectorially add the three accelerations given to OP in steps A and B to get the acceleration of OP with respect to F. Vectorially add the three accelerations given to OP in steps A and B to get the net acceleration, ACCM meaning acceleration of OP with respect to frame F. So all this called the SRC three-step procedure: selection, rotation, combination, or we'll say SRC procedure for acceleration. SRC procedure for what? Acceleration. SRC procedure for acceleration. Okay. So we'll call this SRC procedure for acceleration. Okay. This I'll rub it. Okay. So finally what I'll do, I'll summarize the entire thing. Okay. So final summarization I'll do for SRC procedure. Final summarization for SRC procedure. Final summarization for SRC procedure for acceleration. For SRC procedure for acceleration. First what we'll do, decide SP and OP, which is the selected point, which is the other point. Okay. Now one thing, acceleration of at least SP or OP, one of them should be known. If you want OP, you must know the acceleration of SP. If both are unknown, then there is no use. This procedure is useless. If one is unknown, other cannot be found. At least one of the accelerations of OP or SP must be known. Then draw the line joining SP and OP whose orientation is same as in the problem. Okay. Then give the acceleration of SP to OP. Okay. Then give, first this is selection term. Second, give omega square R to OP towards SP, where R is the distance between OP and SP. And second, give R beta to OP perpendicular to line joining SP and OP in corresponding to sense of beta of M with respect to F. To sense of beta of M with respect to F. Okay. This I'll rub it. And what is the last action which has to be taken? We vectorially combine the three accelerations given to OP in these two steps to get the net acceleration of OP with respect to frame F. Okay, fine. So third action, finally what? Vectorially combine the three accelerations given to OP to get the net acceleration of OP with respect to frame F at the given instant. Okay, this is called the SRC procedure for acceleration. It is called what? SRC procedure for acceleration. Okay, so first what we'll do, we'll decide SP and OP. Acceleration of one of SP or OP should be known. If both are known, then there is no useless. It's useless. And if both are known, then there is nothing to find. Then what we do, we draw the line joining SP and OP such that the orientation is same as that in the given question. Then we give the acceleration of SP to OP. Then we give two more accelerations to OP, omega square r to OP towards SP, and r beta normal to line joining SP and OP, corresponding to sense of beta of m with respect to f. This meaning what? If omega of beta of m with respect to f is clockwise, then we give r beta to OP in such a way that it corresponds to clockwise beta. If sense of beta is anti-clockwise, then we give r beta to OP so that perpendicular to line joining SP and OP, so that it corresponds to anti-clockwise beta. And third action what we have to take, we vectorially combine the three accelerations given to OP to get the net acceleration of OP with respect to frame F. Okay, this is called the SRC procedure for acceleration. S for selection, R for rotation, C for combination. Okay, this is called the SRC procedure for acceleration. SRC procedure for what? Acceleration. Fine. So this is discussed in this fully. Okay. So if you go through it properly, if you understand it, it's more than sufficient. You don't have to take up any other book. You don't have to go anywhere else. You don't have to join any costly coaching institute. If you understand this fully and then you take a problem, I'm sure you will be able to solve most of them. In case you have some problem, you write down the problem in the comment box. Okay. I'll look into it and then I'll try to solve it. I'll try to communicate it to you via some proper way. Okay. So this is all about this. In next session 24, I'll slightly discuss one more aspect of this theory, and then I'll take up numerical problems on this topic. Okay, this I have it here.